Hi, good afternoon. Thank you all for being here. My name is José Manuel, and to try to illustrate the problem that I've been trying to solve for the last 4 years of my PhD, let's imagine a quite plausible situation. Let's imagine that we are all engineers and that as our first job, we've been hired to manage a network, a really big network, a really important network. In fact, it's so important that our boss tells us that not only we have to fix it if it breaks, but we also have to prevent it from breaking. Okay, that sounds weird because that would mean that we have to predict the future. So it's hard, so we turn to the scientific literature. What has been done in order to predict failures on networks? So after a good read, we find that there are 4 open problems. The first one is that in order to predict failures, you have to know the network. This sounds obvious, but it's problematic because that means that you can't generalize knowledge. The second problem is that there are no public data sets that everyone uses, so you can compare solutions. The third one is that most scientists only perform ad hoc solutions for their problems. There are no proposals of general solutions. And the fourth one is that most papers only tackle small scientific problems, which makes sense, but leaves some other problems unsolved, some practical problems unsolved. All of this leads to the fact that there is no current general autonomic solution for proactive failures management. So my thesis has 4 contributions, 4 areas in which I've tried to improve this situation. The first one is whether failures can be predicted. I tried to show this by studying 2 different data sets, a private one that we obtained from a network and a public one from a supercomputer. And I study 5 different machine learning algorithms. When I say machine learning algorithms, this just means 5 different ways of trying to predict the future to show that indeed failures can be predicted. The second contribution ties into the first one. Okay, I can predict failures, but which time period should I observe? Should I take into account the last 5 minutes? Should I use the last hour, the last day? How do I know that? This is something that requires either brute force or expertise. I try to solve this by using a genetic algorithm, which is a fancy way of saying that we imitate evolution to try and solve complex problems, alongside the machine learning algorithms that I talked about previously, to find the lower part of the figure, which are multiple time windows that, when combined, not only optimize the performance of the machine learning models, but also optimize the storage costs. And of course, they are autonomic, so they don't require previous knowledge of the network. The 2 last contributions are really very practical. The third one, or the first practical one, is how do I analyze hundreds of models? If you're managing a really big network, you're going to end up with hundreds of machine learning models. How do I analyze them? The actual methodology is too complex to explain in 4 minutes, but the idea is to study not only the models on their own, but to study the system as a whole. Because there are going to be influences between devices, between types of events that you are able to capture if you study the system as a whole. For example, the figure that I show, it's a correlation chain between events on a network. The white ones are just normal events. And you can see that it leads to a red spot. That means a critical failure on the network. Lastly, the last thing that we propose is how to deploy my prediction models on a network. And we do so by using big data components which are tested, so this leads to a robust and scalable architecture. Thank you.